In this video, we'll begin our discussion of Calculus 3. The section that we are starting on is section 11.1. I'm going to jump right into it. So we are dealing with something maybe you've heard of before. If you've taken some physics classes, Physics 1, you definitely have. We are going to talk about something called a vector. All right, a vector let's start with actually a definition of something else. Numbers that we are used to. Like if we want to talk about area of something, we say the area is 50, or volume or temperature or mass or time. We'd say the mass is 50 kilograms or the time is 8 hours. We'd have a number to measure these things. This thing is called, when we're just dealing with a number, it's called a scalar. So scalar quantities are literally just a number that measures something. Weight could be this way, right? I could tell you my weight, and it's just a single number. Now, there are other quantities, though, that cannot be expressed with a single number, like force or velocity or acceleration, because you got to have a direction, right? You guys talk about this in physics. Speed is a scalar, right? If I'm going 60 miles per hour, I'm telling you how fast I'm going, the speed. Now, if I say I'm going 60 miles per hour in north, then that would be what we call a directed line segment that we could use. That would be some other measurement, not a scalar, right? Because I need two different things. I need how fast I'm going, and I need the north direction. So a directed line segment is as simple as this looks. We start at some P, and we're going to some Q, and there's an arrow telling me which direction it's going. So we have a direction. The arrow tells me which way. And then the length of this actually tells me how much. So like for instance, I just said 60 miles north. So we would have straight up north, and then the length of this would be a 60. And that would tell me 60 miles. So if I had another car going behind me, only going 55, it would be a shorter line segment. One thing I want to point out, and this is the thing I struggled big time with the idea of these directed line segments, and I'm going to go ahead and call it this. This is a vector. A vector has a direction, and it has a length. We use another name for length. We use magnitude. So it has a direction. It tells me which way to go, and then it tells me its length, usually some type of measurement. And it's noted by this, the length. We're going to use to this. We're going to see it a bunch. That means the magnitude of the vector PQ. Right? Directed line segments or vectors that have the same length and direction are equivalent. Okay, so this is, I really want to push this into your brain, because this is something I struggled with when I was in Calc 3. Vectors do not have a position on the graph, like on the coordinate plane. It's not that it lives, there is an initial point, a terminal point, but what a vector tells us is not how to get from this specific spot to this specific spot. It's more of like directions to get there. I know that's kind of confusing. So it's not like from 0, 0 to 5, 8 is represented with a vector. I can move that vector anywhere on the graph, and it'd still be an equivalent vector. So all vectors of the same length and direction are considered the same. That's what they're kind of showing us here, is that these are all equivalent because they have the same length and they have the same direction. It doesn't live anywhere. Like it doesn't, this isn't the vector right here, and then the other ones are transformations of that vector. All these vectors are considered the same because all a vector tells us is direction, which way is it going, and magnitude, the length. Does not tell me from this point to this point. Now, they may write it that way here in a moment. We're going to do some problems like that to show that they are equivalent, but that's just where they placed them on the graph. They can go anywhere on the graph. You'll get used to this idea as we go along. So the set of all directed segments are equivalent to any of them PQ. So these all in the green box are the same as this green one up here. They're all considered to be equivalent. So a couple things I do want to point out. In typeset, if we're typing, vectors sometimes look like this. Boldface. And then sometimes when we write them, because we can't boldface when we write, we put an arrow over U, V, or W. So if it's vector U, you would put an arrow. If it was vector A, I'd say vector A with an arrow. This is key. And this is what I was trying to drive home. It's kind of hard to talk about, but understand that a vector represents a set of directed line segments, not just one. And that's what I was saying. It doesn't live anywhere on the graph. These are all the same. It's the same as PQ above. So we're going to work with vectors a lot. We are actually going to work up to doing functions with vectors, and then we're going to do calculus with vector functions. The good thing is the calculus doesn't actually feel like anything new. I think the most difficult part of this is the graphing, the algebra side of 3 dimensions, where we're headed. All right, let's do an example of just showing that direct line segments are equivalent. So this first example, let V be represented by the directed line segment 0, 0 to 4, 3. Okay, so we have a vector U. I'm going to do it in orange. So vector U. And we start here at 0, 0, and we go over to 4, 3. And then there is my vector. So I'm going to draw it here. All right, I have another vector. All right, it says let U be the vector represented by the line segment 2, 1. So I'm going to plot 2, 1 to 6, 4. 2, 4, 6, 4. That is that line segment. Now, we could use our eyes, right, and say, okay, well, those look the same, but we know at this point that doesn't work in math. Unfortunately, they want to know more. Well, we could do this, and this is just us understanding what it's doing. You're not going to do a whole lot of this for me. But let's talk about the slope of each one. M for the M segment, this will determine, we can use slope to determine a direction, right? It tells me which way to go from a point to another point. Well, the slope here, if I'm looking, okay, it goes up 3 and it goes over 4. So the slope is 3 over 4, right? We can do it that way. Now, if I'm looking at the green one, I go up 3 and I go over 4. So the slopes are the same. So if we were showing that they were equivalent, V and U have the same direction. Now, the other thing that has to be true, if they're equivalent, they have the same direction, and they also have the same length or magnitude. Well, let's just eyeball this pretty quickly. I have this up 3 over 4 thing. I create a triangle here, right? Notice the black triangle. This is a 3, a 4. You could use Pythagorean theorem, but I know that the length of that orange segment is 5, 3, 4, 5 triangle. So I'm going to write that down here. Let me erase all the black. And I know that the magnitude of V, which is the orange one, that's how we write magnitude. 2 lines, magnitude. This tells me the length is 5. All right. We also, if you take the green one and you look at that as a triangle, here's this triangle, 3, 4. The green line is also a length of 5. So thus, V and U are equivalent. So remember, the two things determining a vector is the direction, is it going in the same way, and the length. As long as they have the same direction, the same length, they are the same exact vector. Doesn't matter where it lives. So I could take anything else. I could put it up here, go up 3, go over 4. This vector up here is the same as those vectors down there. There's no certain place that the vector lives. We just use the graph to describe the direction.